Hello and welcome for joining me on this guided project. We're going to use ensemble methods today. And we're going to predict the miles per gallon of classic cars. Here's the link to the data set on Kaggle. And we'll start off by importing libraries. So sklearn, we're going to need standard scalar, and then we're going to need for decomposition, we're going to also use for pre-processing today, PCA. And PCAs are just, they really help. Those standard scalars help the most, but PCAs also do make a good difference in our predictions or making our data more amenable for predictions in our model. So we're also going to use practice using the pipeline today. So make pipeline. This can just help you from having to transform the data. And really, sometimes it saves you coding, like lines of code in your work cell. Sometimes it doesn't, so it really depends on your workflow, but it can be pretty handy to know how to use a pipeline. Okay, so here we're going to do random forest. We're doing miles per gallon, so we're doing a regressor. We're going to do gradient boosting. So gradient boosting regressor. Regressor. And we're also going to do adaboost. Oops, get rid of that. Comma, adaboost regressor. Okay. So, and not the most important, but a really important thing is the train test split as well. So from sklearn.model section, we're going to do the train test split. Okay, let's run that, and then connect and initialize, and voila. Regress, and I need to spell that right. Random forest regressor. So and that's what it was. So I missed an S when I was spelling regressor. And so mistakes happen. You have to go slow and kind of read the documentation. Could I be a spelling mistake because it said not found? And so you have to go slow when you see an error. Just good. I don't like to get errors in these videos, but it does happen, and it's just a natural part of coding. You use the errors to kind of find out, really if you're doing the coding right, and then how to just improve. So really, again, don't be scared of making error. Here we're going to import using pd.read_csv import to and assign to df for our data frame. This data frame is separated. It's not by it's not by commas, it's by semicolons. So we're just going to do sep equals semicolon right here. And then we'll get our data frame. Take a peek at the head of our data frame right here. And so we can instantly see that we have some issues right here. We have displacement and we have a comma though instead of a decimal point, right? So that this is likely going to be a string, but we'll run it and see if our plotting functions will handle this. Another really important thing to do is df.info, and really just important to see our data types. And here we'll be able to see if those commas do in fact make our displacement and horsepower an object. And here we can see that they are. So we will try and put these into our plotting functions, but likely we're going to have to adjust those before we can get a good histogram plot of these, what should be numeric columns, but are likely strings or thought of as strings. So here to be a little bit different, we're going to change the underlying style. So we're going to go matplotlib dot style dot use, and we're going to use BHM today. You can use ggplot as well. I think this just really just makes pandas a lot nicer, so it's a good thing to use. So here we're going to do a loop through our columns. We're going to do different plots depending on which data type it is. So we'll start off by doing for feature in, I like to just, we want to go through all the features and make something that adapts to our underlying features, and we don't have to specifically do some things for or build a workflow specifically for objects or integers, we can just do it all in the same. So here we're going to go df.column. So we're going to loop through all of our column names. We're going to go if df feet, so for each column name is dtype object. So dtype is equal to object. If it's equal to object, we're going to go df feet dot value counts dot and parentheses dot plot kind equals bar plot. So we'll do a bar plot of the value counts. Else, so if it's not an object, it's going to be an integer here in our data set. So if it's an integer, we're going to do df dot plot, and we're going to do kind equals histogram. Okay, and just to give each of our plots a little title so we can understand, you know, what they are, we'll do title, and we're going to give the title our feature, the title that we're looping through each time we loop through these plots. Okay. And so we got our plots right here. And you can see here, let's see. We had horsepower and weight. These obviously, this did not come out to be numeric. These are not. So we're going to have to deal with these because we need to convert these to a string to get them to plot in a histogram properly. Because this horsepower and displacement, again, it's going to take every individual number as an individual character, and that's this. Good. So if we plot these, what we're going to do is, if this is an object, let's plot, so 4 feet, so for short form for feature, 4 feet in df columns, if df feet dot dtype is equal to an object, so for the objects in our data frame, we're going to print df feet dot value underscore counts. Okay. And then I guess one other thing that I did here is just do, if you do alt 2 or alt number combination, you can do different symbols. You can do alt 2, and I believe it should get you the smiley face multiplied by 40. It gives us 40 smiley faces. Just have a little bit of fun, but just to separate each value count. So make it a little bit clearer. You can just do a boring straight line if you want to, but I like to have a little bit of fun. Okay, so 40 of these, and so we can see our data sets, and we can see yes. So these are a problem right here. These are each number is considered an individual value, and that's not obviously going to work. It's not really what we want for our numeric columns. And we have this in a few different, quite a few different of our columns here. We can see it happens over time. So we're going to do column change. So we're going to change miles per gallon, displacement, horsepower, and acceleration. We're going to change all of those. And we're going to do 4 feet in col change, the columns that we're going to change up above, change. We're going to do df feet equals to df feet. So we're like selecting the feature, and then we're going to be returning, kind of copying over what was there, what we're selecting out. And then we're going to take the commas, we're going to turn it into a decimal, and, well, a period, we're going to turn it into a decimal then, and we're going to go df feet is equal to df feet as type float. And so we'll convert all of those into floats, and we can see here we now have floats for those ones that were incorrectly identified as before. So here we'll replot these our univariate analysis here, our univariate plots. So do 4 feet in df columns. If df feet equals object, we're going to do value counts plot kind equals bar, and then down below else, so if it's a numeric one, we're going to go kind equals hist, and then right at the very end here, we're going to do plt dot show. So we're printing out our plot at each kind of time step here, not time step, but each plotting value, and we'll get a nice little plot here. And now we can see here horsepower, weight, acceleration. We actually get distributions here, and I wrote notes on each of the distributions. It would be good to review if you make sure you understand generally what I'm saying. Distributions really become very important, really more important than understanding even what the data represents in real life until you put your model into production. And so, great job. Okay, so here we're going to do pair plot. So for bivariate analysis, we're going to do pair plot. We're going to do df. We're going to give our whole data frame, and we're going to do hue. Oops. we select and replace all of none with hue. Replace all of none with hue. And we're going to do hue to the miles per gallon to get a good context of our target variable. Okay. Okay, so here what we get is a nice pair plot of our numeric features with hue being the target. So we notice some really distinct patterns here. Heavier miles per gallon, really kind of concentrating in certain areas and stuff. It'd be interesting to inspect and really understand when you're building a model. Another really important, I think this goes really hand in hand with pair plots. So we're going to do sns.heatmap, and we're going to put inside our heat map, not the data frame, we're going to put in a correlation matrix. So df.corr. We're going to a note. I think this is kind of almost important when you do this. Just the colors alone are fine, but I think it's a little bit better. And we're going to do cmap equals mac. Just to get a nice little, I like kind of more than the standard colors. And so here we go. We get a heat map. Okay. And we can see kind of, if we're talking about miles per gallon, we have very negative correlations, which is fine, but very strong negative and very positive correlations right here. Moderate kind of a correlation with acceleration, but a little bit stronger with model. Okay. Here what we're going to do is plot another histogram. What we noticed when we were inspecting the distributions is there's a lot of values concentrated around 0. And so just on a hunch, I wanted to inspect how many values are actually 0. And we noticed there's 9. So miles per gallon can't really be 0, can it? And so because this is the target, there's not really, we could fill this in some way, but we really shouldn't because it'll add just so much bias, and really we could make it so that our model predicts it well, and that just really adds a lot of bias. It's better just to drop it. So when we come down to this one right here, I'm going to do miles per gallon not equal to 0. So when it's not equal to 0, I'm going to copy this and I'm going to assign it to df, and we can see now we go from 406 to 390. Okay. So treating some outliers and the other ones, we're going to go plot the horsepower here. When we're plotting the horsepower, we notice that we have some outliers here, so we're going to clip these. So we're going to clip here, and we'll do lower and upper. And you can play around. This is something I think it would be really good to experiment with, a good opportunity. What are the good boundaries to set? But really outliers will be pull the coefficients to what is good for outliers, and therefore might not be good for a whole data set. And so it's good to trim them. So trim them here, plot it now, and we can see we got rid of the outliers. Do the same thing for weight. So let's see, we're going to do plot. So we're going to go kind, and we're going to go hist, kind hist, and we're going to do 30 bins. So bins equals 30. Plot that out right there. We're then going to go clip again. We're going to truncate this, and we're going to go upper equals 4750. Okay, run that, and then we look at the histogram plot again. We can see we truncated them. We don't really have any outliers anymore. So, okay. So then looking at acceleration. So acceleration, we do see we have kind of outliers on both sides here. Almost normal distribution, but we're going to truncate those in a little bit. So here in this workflow, we're going to do df acceleration column is equal to df acceleration column dot clip lower and upper. Okay, so we'll run that, and we'll look at this histogram here. Okay, we can truncate it in. We don't have so much. Those outliers weren't as strong, but just again, it should make our model more predictive as well. Okay, so here we're going to do dimension reduction. We're going to do this because we're going to make one hot encode this, and this is going to create individual columns for 3 and 5 cylinders. It would be nice if those were bigger and we could group those together, but those are so small. I'm going to group them together with the next largest one is going to be 6. So what we're going to do here, just to inspect it first, so we're going to do value counts dot plot kind equals bar. Okay, and the value counts there. Okay, so we're going to what we're going to do here is we're going to replace cylinders column with 3 and 5. We're going to replace that with 6. So everything now is going to be 6. We look at that again, value counts kind equals bar. You can see here now we only have 3, and so when we want to hot encode this, it'll work a little bit better. To bin some of the continuous, and specifically the year, I think is a good column to do this with. So really the value might not be continuous, it might kind of fluctuate up and down and stuff. And so year, I think, is a good one to bin. It's usually a good candidate here. So we'll do pd.cut. Then notice that we're giving it the series, the column that we want to bin. We're going to do bins our outside edges. So if we have 4 bins, we're going to have 5 outside edges, but we're going to need 4 labels right here. So we have, if you have 1 bin, you have 2 outside edges, so you always have 1 more outside edge than you do labels here. Oops, let's create another one right there. So we'll cut that, and then we'll look at our labels. So again, that should be an S right there. See, don't overreact when you make errors. Just keep going. Anyways, so now we have our model category that we got from pd.cuts. So now we're going to use that in create one hot encoded dummies from that. So we're going to get underscore dummies. And here we're going to go we're going to give it df or full data frame, and we're going to say the columns to do, and we want to do cylinder origin model category. And here we go. So now we have 17 columns. We've gone up quite a few. We've one hot encoded them, and you can see the 1s and 0s here. When each one of these 4 columns would be true, there's only going to be 1 for each of them. And so we have now one hot encoded, and our model can develop coefficients on each one of those. Okay. So heading into our modeling section. So here what we're going to do is we're going to do features equals a list of our features. Target equals our target that we're going to predict today. Capital X equals df features. And so just make sure I run this list up here above. And then we're going to do Y equals df targets. And so we're signing that. And I like that because then you can comment out a name. Let's say I want to see if I really need acceleration. It hasn't really seemed like it was going to have a high correlation. So see without, you can just comment it out and kind of run. Everything will work with the same workflow. So it's kind of nice. So here when we're losing that, we're going to do X train, X test, Y train, Y test, train test split. We're going to give it the large X, which is just meant to represent more than one feature, small y because we're predicting one column, test size 0.3, random state. So there we go there. We print those out. You can see here we have 15 columns and 1 target. Okay. So here we're going to do assign our standard and initialize our standard scalar and our PCA to use in our pipeline down below. So we'll initialize those. And what we'll do, so we want to standardize first because PCA is sensitive to distance. So we want to standardize first. So this should be STD. This should be the object that we've assigned this to. ST scalar. And then we want to put it through PCA. And this is going to be random forest regressor. Okay. So then we'll go dot fit as we're initializing this pipeline, essentially our model, but we're going to do small transformations or large transformations as we pull it into our model. But that way we don't have to do those transformations on the underlying. We're not saving those changes that we do. It happens kind of organically in our model. And so here what we're going to do is we've assigned that to RF. So it's just our model. So I'm going to call it just our model RF. RF does a little bit of transformation as it's pulling the data in, but it is still just our model. So here we'll do rf.score, give it X train and Y train. Again, we've never standardized X train or X test, but now we're just pulling them in. And we got to spell score correctly though. And we're just pulling them into our data set here. Got a 97, which is pretty good. Okay. So we'll predict now on our values, and we're going to use that down in the residual plot in the next one. So predict, so rf.predict, xtrain, xtest, and get our train and test predictions. We'll then go resid plot, and we'll go x is equal to y train, y is equal to y our predictions, set title equals to the residual plots. Okay. Need to really bad speller at the end of this workflow. This is a good workflow. We did a lot today. So we can see here really our miles per gallon, our true values on the bottom, and our what we predict is on left. And you can see we start to make a lot more mistakes on the higher values of what we were trying to predict. And so I really think this is just a really good to look at and understand where you're making mistakes in your predictions. But on the target, we seem to make predictions kind of not on the high ends, closer to 30. We really kind of go the other direction of where we're making mistakes on our training set. So really interesting if you want to learn how to improve and understand how to improve your model. Really good to inspect that type of data set and what you could do and change in your pre-processing to help with those. And outliers might be a secret to helping with our predictions. So because we saw the values happen on one end of the spectrum. Anyways, okay, so here we want to go GB, gradient boosting, is going to be equal to make underscore pipeline. We're then going to do the same thing. Standard scalar, PCA. We're then going to call gradient boosting regressor next, and we're going to dot fit as well with our training data. We're going to then call down below GB, gradient boosting our model, dot score, gradient boosting dot score for a testing set, assign those, 98%. Gradient boosting is usually my favorite. It always just seems to do really, really well. We'll do the predictions as well. Down below, plot the residual plots, and then we want to put the title on it, so we'll just go dot set, and then title equals residual plots. So do that one, then do the same thing for our test set as well. I think you can just see by looking at this, our predictions seem a lot more concentrated, and they don't seem so extreme. We're going up to 8. It really doesn't seem like they're quite so missing. They're still, I feel like we're still kind of missing in the same area though, but we're doing, I think, a little bit better overall with our predictions. They feel a little bit more tighter and closer to the well, no error, the 0 error mark. And then doing the last one, we're going to do adaboost. So yeah, ADA equals to make pipeline, standard scalar PCA, adaboost regressor. Adaboost regressor will fit that. We'll then get the score, we'll predict on that, do the residual plots, and then we'll do the residual plot for the testing set. Okay, and so you can see we did get a little bit, our score, it's not quite as good with this. We can see that the errors are a little bit more spread out. We're making some pretty big, large errors over here on this side. So just to kind of do the last finish off our workflow, so we'll do TR underscore scores, and then we're going to put in a list of our score underscore trade, what we've done before. Score underscore, we're going to do gradient boosting, and then score underscore add. Okay. And here what we're going to do is we're going to do, what was our first one? Was a random forest. Gradient boosting, adaptive boost. So we've done 2 lists of our scores. We've done 1 list of our models. We're then going to put them into a dictionary. So TR scores here. We put that, and these key values right here are going to essentially become our column titles. So then we put this dictionary down into this data frame down below, data frame. We're then going to put the dic scores into this, and we're going to set our index to the list of models up above. Okay, and then we're going to sort the values, and we're going to do ascending equals false. Okay, so dic, and just notice that you can see the little red kind of warning sign right here. I forgot to do the plural because I like to do, there's more than one thing happening here, so I like to put the S. And you can see here we got the test scores. The random forest did the best in the test scores. Gradient boosting next, second close, but gradient boosting did the best on the training scores. So maybe there is some ways you can play with the, we did the best on the random forest. You can play around with different hyperparameters here and see if you can improve upon the model. I experimented a little bit, and the best that I could do was almost as good as what was achieved in this one, 0.001, close to it. See if you can do better than me. So thank you very much for joining us on this guided project. Have a great day, and see you next time.